Welcome to The Explainer. Today, we are heading straight into one of the universe's biggest mysteries, black holes. Yeah, we're going to peel back the layers on what these things actually are, how they form, and the really deep questions they make us ask about, well, reality itself.
All right, so let's just get one thing out of the way right from the start. You've definitely seen it in movies, right? This idea that black holes are basically giant vacuum cleaners just roaming around space, sucking everything up. But you know what? The truth is so much cooler and honestly a whole lot weirder. See, a black hole isn't really an object that pulls things in. It's a place. Think about it like this. It's a spot where a ton of mass has bent the very fabric of space-time so much that every single path, for light, for a spaceship, for anything, just leads inward. So to really get it, we've got to ditch that whole cosmic drain idea. Instead, let's take a little tour of a black hole's structure. We're going to start from the outside and work our way in, exploring all the bizarre regions that make these things what they are. Okay, let's do it. Let's dive right into the anatomy of a black hole, layer by bizarre layer. I want you to imagine you're in a spaceship and you're getting closer to one of these gravitational monsters. You're at a safe distance, but what's the first thing you'd actually encounter?
Well, your first big landmark is the most famous part of all, the event horizon. Now, this isn't some physical wall you could bump into. It's more like an invisible boundary, a one-way door in space-time. The second you cross it, the speed you'd need to escape is faster than the speed of light. And since nothing can do that, there is absolutely no going back.
And just to give you an idea of the insane density we're talking about, get this. If you could take our entire planet, all of Earth, and crush it down into a black hole, its event horizon would be just 17.4 millimeters across. I mean, think about that. The entire mass of a planet packed into a space smaller than a coin. Now, if you could cross that event horizon, every single path forward would lead to one place, the very center, the singularity. This is it, the end of the line. It's a point where density and the bending of space-time just go infinite. And at that point, everything we know about physics, all our rules, they just stop working. But hold on, before you even get to that point of no return, you'd fly through something called the Photon Sphere. This is a region where gravity is so powerful that particles of light get snagged in its grip, forced into these unstable orbits around the black hole. And that's it. That's the reason we see that incredible bright ring in all those famous black hole pictures. And if the black hole is spinning, which most are, there's an even weirder region called the Ergosphere. Here, the black hole's rotation is so intense, it literally grabs the fabric of space-time and drags it around with it. If you were inside the Ergosphere, you couldn't stand still, not even if you tried, because space itself is in motion. So look, here's the big takeaway. A black hole isn't just one thing. It's this incredibly complex structure with all these different parts, the Ergosphere, the Photon Sphere, the event horizon, and that singularity at the heart of it all. Each one is a place where physics gets pushed to its absolute breaking limit. Okay. So now that we've got a better grip on what a black hole actually is, let's talk about the different kinds we see out there in the universe. Because, they're not all the same. They come in a whole range of fascinating sizes. Astronomers usually sort them by mass. So you've got your stellar mass black holes, which are basically the dead husks of giant stars. Then you've got the supermassive ones, the titans, like Sagittarius A, sitting right at the center of our own Milky Way. And then there are these other weird ones, like the hard-to-find intermediate mass black holes, and even theoretical ones that might have formed right after the Big Bang. But here's where it gets really interesting. Our theories about how stars live and die, they predict something weird. They predict there should be these mass gaps, ranges where black holes just shouldn't be able to form when a single star collapses. And that has created a really fun puzzle for scientists. The biggest one is called the pair instability mass gap. The physics gets a little dense, but basically, for stars in a very specific mass range, their core gets so unbelievably hot that it starts creating matter and antimatter. This kicks off a massive thermonuclear explosion that's so powerful, it just blows the star completely apart. No leftovers, nothing to collapse into a black hole. And yet, we found them. We have found black holes right in that forbidden zone. So how did they get there? Well, the best theory we've got is something called hierarchical mergers. The idea is that they aren't born in the gap, they grow into it. In really crowded star clusters, smaller black holes smash into each other and merge, creating a bigger one. And then that process just keeps repeating, building them up, generation by generation. And this isn't just a theory. We have proof. Back in 2019, our gravitational wave detectors heard a signal. GW 190521. And what was it? It was the sound of two smaller black holes merging to create a brand new one with a mass of about 142 times our sun, smack dab in the middle of that so-called mass gap. So that leads to a pretty obvious question, right? If these things are invisible, if they swallow light, how in the world do we know any of this is real? How do we see something that, by its very definition, you can't see? Well, one of the biggest breakthroughs ever came in 2019 from the Event Horizon Telescope. This wasn't just one telescope. It was a network of radio telescopes all across the globe, linked together to create one virtual Earth-sized observatory. And with it, they did the impossible. They took the first ever direct picture of a black hole shadow all the way in the M87 galaxy. And at the very same time, observatories like LIGO and Virgo are giving us a completely new way to experience the universe. They don't see light, they feel the universe. They listen for the tiny ripples in space-time itself that are created by huge events, like two black holes spiraling into each other and crashing together. These discoveries have been absolutely incredible. I mean, they've changed everything. But they've also shoved us right up against the edge of what we know, and they've revealed this deep, fundamental clash in how we understand the universe to work. And this brings us to one of the biggest fights in all of physics. See, Stephen Hawking showed that black holes aren't forever. They slowly evaporate over trillions of years. But his math also suggested that when they disappear, everything that ever fell into them, all the information about it, is just gone, destroyed. And that's a huge problem because it violates a sacred fundamental rule of quantum mechanics. Information can never be destroyed. This is the famous black hole information paradox, and it's one of the biggest unsolved problems out there. One possible way out of it, which Hawking himself actually helped come up with, is called the soft hair theory. It's the idea that information isn't actually lost. Instead, it gets sort of imprinted on the event horizon as tiny quantum fluctuations, and then it slowly leaks back out as the black hole evaporates. And that really brings us to the final mind-bending thought here. Black holes, it turns out, aren't just objects out in space. They're cosmic laboratories. They're the one place in the universe where our two best theories of reality, general relativity for the big stuff, and quantum mechanics for the small stuff, smash into each other. And in doing so, they force us to question everything we think we know, and to search for an even deeper truth about our universe.